Hi guys, welcome back to the channel. In this video we are going to discuss MOD-10 counter in detailed discussion. So there are two methods to implement this MOD-10 counter, means both the up counter and down counter we are going to see in this video. So let's get started. So these are known as full modulus counters. We have mod 4, mod 8, mod 16. This is the general cascading of the flip-flops. So we are going to identify from these full modulus counters how we are going to obtain our required modulus, that is mod 10 in this video. So let's see how to do that. These are the truth table for the full modulus counters. The first one is starting from 0 ending at 3 and again going to 0. So it is counting 4 states, that is why it is known as mod 4 counter. The second one, if you observe, that is mod 8 counter because it can count up to 7 states. Means total 8 states I can say, starting from 0 ending at 7. So last one if you see, that is mod 16 counter. For this we are going to use the 4 flip-flops. Then how we are going to generate the mod 10 counter? So with the help of 4 flip-flops only, means the third truth table is helpful for that. So let's see how to do that. So the first step is to find the number of flip-flops. So we understood the number of flip-flops are 4 because starting from 0 and ending at 9. So total 0 to 9, that is total 10 states. So this is known as mod 10 counter. It is also known as the BCD counter. So BCD means binary coded decimal. So it is also called binary coded decimal or mod 10 counter, REPL, mod 10 counter, anything we can call it as. So as you can see here in the mod 10 up counter, we have to have in the sequence, that is starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and again it will go to 0 and again it continues the sequence. So this is the up counter, mod 10 up counter. So if you see clearly, we are using 4 flip-flops but we are not utilizing all the situations. So we are going up to 9 because that is total 10 states and we are leaving the up from the remaining states, that is 10, 11, 12, 13, 14, 15. So we are the left remaining things are we are leaving. The remaining 6 we have left, so that we are going to consider only 10 states. So we are going to last up to 9. So whenever if you see the 10th position, that is 10, that is 1010 in binary and 10 in decimal, whenever you see that, you are going to change or you are going to apply some logic on 10, so that you are going to obtain or you are going to pass that logic to the clear that as 0, so that you can have all the flip-flops as 0. So as I mentioned, there are two methods to do or implement the mod 10 up means the counter or mod 10 counter. So in the second method, we are going to use the manipulation with the help of NAND gate. So we are going to manipulate the 10 output and we are going to obtain or we are going to have the 0 to the clear outputs. First one is normal general method that is used in the every situations. So let's see the first general method. These are the two methods that I am speaking about. So first one is using K-map. Second one is a simple logic with an AND gate. So second one is very simple, often used or not used. So first one we should know, very important. First one is, so that is with the help of using K-map. So if you observe, we are going up to 9 only. We are not using the 10, 11, 12, 13, 14, 15. So we are going to have a truth table and we are going to have a K-map. So let's see how to have a K-map. So if you see clearly in the K-map, I have also added a column called reset logic Y. So this is the logic circuit that we are going to add to the sequential circuit, that counter. We are going to add this using K-map rules and we are going to obtain the output expression Y. So how we can take or how we have to have the output Y. So starting from 0 to 9, because that is the mod 10 counter, right? So that is the thing that we are going to have total 10 states. So remaining all things output would be Y. That is starting from 10 to 15 outputs would be Y. So now we are going to place all these things in the K-map and we are going to start grouping. Because of we have total 4 variables, that is A, B, C, D. These are the outputs of flip-flops in the counter. So we are going to place all of them in the K-map. It will looks like this. And the output Y is equals to sigma. That sigma notation also you can see over there. So we have left. Now you can see we can make a group of 8 elements and we can make a group of 4 elements. So let's do that. So after making groups, you can see like that. We can make a group of 8 elements, that 8 elements. And another group is group of 4 elements, that is 0, 1, 8, 9. So that is corner grouping. After making that, you are going to get the output expression Y, that is D bar plus C bar B bar. So what is ABCD? ABCD are the outputs of the each and every individual flip-flop. So totally we are using 4 flip-flops. So we had 4 outputs ABCD. So this B bar, C bar, D bar is already available in the flip-flops. So we are going to connect this combinational circuit so that we can have the output Y. We can connect to clear output. And one more important thing, for discussing any of the required modulus counter, our required modulus counter is here 10, mod 10 counter. So for that we need to start with the full modulus counters. So here, as we are using 4-bit flip-flop, we are going to start with mod 16 up counter. So this is that, with the including clear signal as well. Because after the ninth position, we are going to clear all that. So for that we need the clear signal, right? So after, if you enter the 10th position, means 1010, you are going to again go back all outputs as ABCD as 0000. Already we have the output expression y, that is d bar plus c bar d bar. So just we are going to join the things with the help of an AND gate and OR gate, because that is the thing that is there. So we have already b bar, c bar, d bar with the help of flip flops. So this is very simple but very important. We can also implement any kind of logic that we want with the help of this K-map rules. So in the same way we can implement mod 5, mod 6, mod 8, mod 10, anything that we want, because this is full modulus counter. With the help of the truth table only we are going to decide this. So suppose if you want up to implement mod 6, so just put all the ones up to the 6th position and leave remaining all things as 0. So that is the simple thing. So from that, by filling the K-map, you can get output expression y. So in the same way you can do that also, mod 6. Now we are going to implement the BCD counter with the help of the NAND logic. So what is meant by NAND logic? So if you have all the inputs that has 1, the final output would be 0. That is the thing that we have saw in the logic gates. So if you have, so suppose if you have 10, so I said in that truth table only. So we are going to break, whenever you see the 10, we are going to break the circuit or the logic that we are going to break there, and again you are going to traverse the Q0, Q1, Q2, Q3 as again 000. So that is our main aim. Your 10 is 1010. So let's see how to have all the inputs as 1111 and how to produce the clear output with the help of the NAND gate. So for that also we are going to have the first of all mod 16 counter. In this we will be going to make some changes so that it becomes the mod 10 counter with the help of NAND gate. So let's see how to do that. So we are going to connect all the outputs Q0, Q1, Q2, Q3 to the NAND gate, and we are going to have the NAND gate output as 0. So for the NAND gate output as 0, we are going to have the Q0, Q1, Q2, Q3, all the outputs as 1, 1. But we have 10. So 10 is not all ones. So 10 is 1010. So the first Q0 is directly 1. So we can connect directly to that NAND gate simply. The next one is the Q1 output. So we are going to connect the Q1 output directly to the NAND gate, and we are going to produce output 0. Wait. But Q1 is 0. If you connect Q1 as 0, so that becomes our whole output as NAND gate as 1. So we don't want that. So for that also we are going to connect the Q1 to the NAND gate with the help of NOT gate, so that it becomes our output 1. So I hope you understood this. The next one that we are going to connect is Q2. So as Q2 is 1, we don't have any problem, so we can connect directly Q2 to the NAND gate. So the final thing is that we are going to connect Q3 to the NAND gate. So Q3 is 0. You can observe the 10 is 1010, right? So in that we are going to have Q3 as 0. So you are going to have in this also a NOT gate, so that it will invert 0 to 1. So you can see the 4 ones, all the 4 ones is 0 ones. So it becomes the output for the NAND gate is 0. So that 0 is the clear 0, that is applied to clear. It will clear all the outputs at a time. When it becomes 1 means the 10. So when it sees 1010, it becomes all the output clear as 0. So there are many ways to represent a single circuit. So this is the same circuit, but we have a small change over here. So instead of having NOT gates, so already we had the Q1, but we had Q1 bar also. So instead of having 0 directly, we can have the 1 also. You can see down also there. So if you have Q1 as 0, so take Q1 bar. So if you have Q3 as 0, take Q3 bar. So that is the thing. A small simple trick change that we have made whole the changes. Instead of taking NOT gates, we have simple saved our logic gates with this representation. So I said before only, there are couple of ways to represent a single circuit. So this is another representation of that same circuit. So we are not going to represent the zeros, just we are going to connect the Q1 means the Q0 and Q2, because those are 1 ones, right? In the 10, that is 1010. If you observe that is Q0 and Q2 are 1 1. So that we are going to connect only Q0 and Q2 to the NAND gate. So both are ones, it becomes output 0. We are applying the output 0 to the clear, again it becomes all outputs as zeros. So now you might get a doubt, why we are not connecting Q1 and means Q3 to the NAND gate. So without connecting Q1, Q3 also, how it is behaving as mod 10 counter. So let's understand with the truth table. So if you observe in the truth table, that is Q0 and Q2. So in the whole truth table, the first ever that we have saw, that is q0 and q2 as 1 1. So show me that. So the first situation where you see the q0 and q2 are 1 1. So the only 10th position, the first time that we see the q0 and q2 are 1 1 in the 10th position only, the first time. So that is the reason we are going to apply only the q0 and q2 to the NAND gate, so that we are going to obtain our whole logic as 0. So in that situation we are going to consider the q1 and q3 as 0 0 only. So that is the thing that is written over there. So next thing that we are going to see is the MOD-10 down counter. So down counter is nothing but you are just starting with 15 and ending up to the last one. Means last one means what? Up to we are going to calculate the 10 sequence. So 10 minus 15 what? That is 10. So we are going to go up to 6. If you see the 5, so 5 is our main logic. So whatever we done in for the 10th situation, as we saw, that is 1 0 1 0 situation, what we have done up to now, the same situation is happened for the 5, that is 0 1 0 1. So for that 5 we are going to apply some logic, so that we are going to have our output logic. Or I can simply say, whenever you see 5, then again you are going to go to 15. So here 15 means 1 1 1 1. So I said before only, whatever may be the small circuit or the middle in between circuit that we are going to construct, for that we need to have the first full modulus counters. So this is the full modulus 16 counter I took. So in this I did not take Clio, I took preset bar, because we need here presets. Because again, suppose if you starting from 15, you are going to end up with suppose 6. So whenever you see the 5, again you are going to come to what? 15. 15 is what? 1 1 1 1. So that is not 0. That is not 0 0 0 0. So we are going to again go to 1 1 1 1. So for that situation we need to reset our all flip flops to 1, not 0. So for that only I took preset, not clear here. So this is active low inputs, that is preset bar, not preset. So you can see bubble in the flip flops also. Then how we can construct the MOD-10 down counter? So this also have some bunch of couple of ways to do that. So the first method is, as we all saw in the up counter only, the same thing that we are going to follow. So simple thing, that is 5. 5 means what? 0 1 0 1. The first one itself is 0, that is q0 is 0. So we should connect the NAND gate, so with the help of a NOT gate. So that becomes our output, the first one. So for that we need to have the NAND gate as the whole output as 1. So but we need to have the NAND gate output as 0. So if you have the NAND gate output as 0, we have bubbles, so that both bubbles will be cancelled. Means the NAND gate output is 0, and again you are going to invert with the flip flop you are attached a bubble, that will invert as whole output preset bar as 1. In the same fashion, now you are going to join the q1 directly, because the q1 is 1 here for the 5. If you observe the q2 should not be joined directly because that is 0, so you should have a NOT gate after that. So finally in the 5, that is q3 is 1, so with that we can connect directly. So you can see the outputs, that is q0, q1, q2, q3, that is 0 1 0 1 we are applying, but the output is, after that you are going to have the NAND gate output as 0. So 0 will be again toggled by the all flip flops, that is 1. So again you are going to reach all the flip flops as 1 1 1 1, because 0 will be toggled by that preset bar. Or if you don't want the NOT gates, you can simply connect with the bars also, because bars are readily available for us. So if that is the two cases, that is the q0 bar we can connect directly, and q2 bar we can connect directly, as you are seeing there. So finally, instead of taking preset bar, we can simply take the preset and remove all the bars in the flip flops, and you can have an AND gate. So if you have AND gate, so simply just remaining circuit all would be same, but remove the bubble for the NAND gate, that becomes NAND gate. Sorry, AND gate. If you remove bubble for the NAND gate, it becomes AND gate, and remove bubbles for the all flip flops also. So if you simply have all the outputs, means all the inputs for the AND gate would be 1 1 1, and the output would be also 1, and simply we are applying 1. So all the outputs, because preset is 1, all the outputs become 1 after this 10th state. So if you simply compare both of the K-map method and the NAND logic circuit, so which one is better? So the first, if you see the aspect, so regarding reset derived from, so if you consider the expression that we have already seen, so the second one is direct gate detection, that is q1 and q3. So we are connecting NAND gate directly. So flexibility, so the K-map based logic is highly flexible state control. Means majority of the cases K-map is used. For the understanding purpose, I also explained you the NAND gate also. So limited resets and hard wired states. So if you see the optimization, yes, where K-map. So there is no optimization for the NAND gate. So last is complexity. So K-map based is circuitry is somewhat complex, higher complex, because there we need multiple logic gates like AND gate, NAND gate, OR gate. So that kind of logic gates are used over there. But in the NAND gate logic, just we are using the NAND gate, that's it. So if you want more high precise means high precisity or exact values, you are going to use the K-map. If you want low precise but we need to have means low cost, low complexity, if you want, you can go with the head of NAND gate logic. This is MOD-10 state diagram, you can see over there. So that orange line indicated the up counter. The blue lines are indicated the down counter, you can see over there. Basically starting from 0 and end at 9. And if you are dealing with the down counter, starting with the 10 means 9 and end up with 0. Often in the internet you might see these kind of two pictures in representation. So I have explained these two kind of representations, why we are doing with the two representations. So their aspects, where we are going to use which one, I also explained that whole concept also. So I hope you understood this video. Thanks for watching up to now.